In this video, we solve problem 8.1.17 from Essentials of Statistics 6th edition by Mario Triola. The problem statement says that the test statistic of z equals 2.10 is obtained when testing the claim that p, that's a population proportion, is greater than 0.4. In part A, we're asked to identify the hypothesis test as being two-tailed, left-tailed, or right-tailed. Then we're asked to find the corresponding p-value and then using a significance level of alpha equals 0.05, we're asked whether or not we should reject or fail to reject the null hypothesis. So let's start by answering this first part. It says, identify the hypothesis test as being two-tailed, left-tailed, or right-tailed. We can tell right away that because the claim involves this strictly greater than sign, that it's a right-tailed test. So we always start by stating the claim. Oops. In this case, the claim is p is greater than 0.4. Now, it does not contain the condition of equality, so I will write another hypothesis that does contain the condition of equality. This is the alternative hypothesis. The one with the condition of equality is the null hypothesis. And then when I'm looking at this, since I see that that's not a not equal to sign, but it's a greater than sign, I know it's a right-tailed test because that arrow always points in the direction of that tail. So this is how I would typically draw it. Here is our sampling distribution. Of the sample proportions, p hat, and the mean of the sample proportions is equal to the population proportion. And in this case, we're assuming that the population proportion is equal to 0.4. So we're assuming that that null hypothesis is true. And so that mean is 0.4. Now, because of this greater than sign, as I said, the arrow points to the right, so it's going to be a right-tailed test. So that's our answer to the first question. And then we're asked to find the p-value. Now, when you're finding the p-value, you have to determine what type of test first, if it's right-tailed or left-tailed. Then that's going to allow you to determine the p-value. If it's right-tailed, in our case it is, the p-value is the area to the right of the test statistic. So our test statistic is z equals 2.10. So if this is the sampling distribution of sample proportions, we could convert that to a standard normal distribution with a mean of 0 and a standard deviation of 1. So these would be values of p hat, and over here we'd have z-scores. Now we're looking for the area to the right of z equals 2.10. And that z equals 2.10, that corresponds to a particular value of p hat. If we had p hat, we could use that to calculate this test statistic. And capital P is that area to the right because it's a right-tailed test. And the area to the right of that particular value of p hat is the same as the area to the right of z equals 2.10. Okay, so I want the probability that z is greater than 2.10, but my table does not include areas to the right, it only includes areas to the left. So in order to find this area to the right, I will take 1 and subtract the area to the left of z equals 2.10. And this I can find either using that table of values, table A3, or we can use Excel, or you can use other technology to find that area to the left. Let's see. I think I will show you how to do all three. Well, actually, both of them, not all three. I'll both options. So here's method number one. We could use table A3. Or it's actually, I think, table A2. A3 is our student t distribution critical values, I think. So I will share my table with you. Okay, and I want the area to the left of z equals 2.10. Okay, and that's on the far right of the graph, so we know we want to go to positive z-scores. The area to the left of 2.10 comes from going down this column. There's 2.1. 2.10 is right here. Oops. And so I want that area, which is in the body of the table. That's 0.9821. And we're subtracting that from 1. Okay, so 1 minus 0.9821, and that's going to give me the area to the right. So this area was 0.9821, and this area, which is the same as our p-value, is 0.179. So that was the answer to part A, and that's how we do that using table A2. Now we can also use Excel. So let me show you how to do this using Excel. All right, so I'm going to zoom way in. Now, if I want the area to the left, that is a standard normal distribution. I can type equals here, and then I'll type norm.dist, open parentheses, and it's asking for the x value, which in this case is a z value. That's 2.10. The mean of a standard normal distribution is 0, and the standard deviation of a standard normal distribution is 1. And then when it asks if we want the cumulative distribution function, that's the areas to the left, I'm saying yes, true. And so I get 0.9821, which is what we had in our table approximately. And then the area to the right is 1 minus that. And so we get the same answer. And if I round to 4 decimal places, there we go. And I get 0.179, which is the same value that I got using my table. So we can do this, or we can use this function. So we'll use Excel. In that case, this probability, or the area to the left of z equals 2.10, can be found this way. You use the norm.dst function, and then inside you'll put 2.10 and 0 for the mean and 1 for the standard deviation and true for that fourth option, which just means you're getting area to the left. They don't have an option for area to the right. So once you find that, you can infer the area to the right by subtracting from 1. Okay, so that's our p-value there. And now in part C, we're asked whether we want to reject or fail to reject the null. Well, I guess we need to know, oh, there's our alpha. We need to know what our alpha is. So in this case, alpha is 0.05. And we're just going to compare our p-value to 0.05. So for part C, we'll say that since p, which is 0.0179, is less than 0.05, which is our alpha value, since that's true, that means the probability of getting that p hat value that we found is about if I convert to a percentage, 1.79%. So the chance of getting a p-value that is that extreme or more extreme than that, p-hat value that is that extreme or more extreme than that, is 1.79%, and that's less than 5%. So that's very rare. And so we're going to say, if it's a very rare event and it's happening, maybe the underlying assumptions that we started with are incorrect. So we assumed that we were looking at a sampling distribution of sample proportions, and the mean of the sample proportions is equal to the population proportion. Since this is since it's so rare to get a p-hat that extreme, when the true population proportion is 0.4, we're going to reject that idea that p is equal to 0.04. So we're going to say, since p is less than alpha, we reject the null, which says that p is equal to 0.4. Again, this is just a manifestation of the rare event rule. It's just saying a value of p-hat this extreme is so rare that we're going to say that maybe our assumptions are wrong. If assuming that this was equal, our population proportion was equal to 0.4, meant that the value of p-hat that we were getting was extremely rare. And we're saying, what do you mean by rare? How rare? Well, the probability is less than 5%. Well, then in that case, we're saying maybe our initial assumptions were incorrect, and we reject the null hypothesis. That's the reasoning that goes on behind that. Now, if you're looking for just a hard and fast rule, you may have heard this. If p is low, the null must go. There's your mnemonic device. So reject the null. Or if p is high, the null can fly, or the null will fly. So there's a mnemonic that will help you remember, but I would rather that you think of this in terms of that rare event rule for inferential statistics, that we're saying that there's an extremely small probability that p-hat takes on that value when the true population proportion is 0.4. And then we're saying if it's such a small probability, but it's actually happening, maybe our initial assumption that the population proportion was 0.4 is inaccurate. So we should reject that. Okay, so that's how we solved that problem.